Hello everyone, welcome to the second part of Jenkins models. In this video, we will go over the ARIMA model. Okay, so far we have discussed autoregressive models, ARP. Well, remember that P refers to how many periods before we consider. So if P is equal to 2, in our model, we're going to consider the two previous values, yt minus 1 and yt minus 2 to make the prediction of the next value. In the moving average models, MA with order Q, now instead of using the values of the series, we use the errors, the residuals from previous periods. So Q defines how many periods before how many residuals we're going to consider from previous periods. Okay, so typically we use autoregressive moving average and ARMA, which is the mix of these two, when the model when the data is stationary. So quick reminder to test if our data is stationary or not, we use the Dickey-Fuller test, the augmented Dickey-Fuller test, to check that where the null hypothesis is that the time series is non-stationary. So when we reject it, then the time series is considered stationary. Okay, so in some cases, when we have trends, meaning that our data or our time series is non-stationary, so in that case, we cannot use these models. So we need to refer to ARIMA, which is the most comprehensive model in box Jenkins that includes like all possibilities. It can model, everything because it has three parameters: P for the autoregressive components, Q for the residuals that we considered before, and D, which is a new term, and we use D for differencing to find difference. So what is the idea of D? The idea is to make the series station. D is like how many times we need to find the difference of the time series until our time series is stationary. So let me give you a little bit more intuition about that. So if we're given a time series, you plot it and it looks non-stationary, so you will perform the augmented Dickey-Fuller test. Then if we do not reject the null hypothesis, right, then it implies that it's non-stationary, so we need to differ to find the difference in our time series. So what is that? D1 is the most popular differencing. So it means that, remember that originally you have yt, right? So when you apply D1, you're going to find the difference of your time series. That means that this is yt, so you will do yt minus yt minus 1. So it's the difference. This means that you take the value that is in the second period minus the value in the period number 1. You do the same with period 3 minus period 2, period 4 minus period 3. That's how you find the difference. Now, okay, this is D1. When do you have to apply D2? So once we find the difference, then the idea is that you take the series of the differences and you need to apply the augmented Dickey-Fuller test, you need to plot them again. So if it's stationary, after differencing one time, if it's stationary, you stop right there and D is equal to 1. But if your time series is non-stationary, even after the differencing, then you need to find the difference one more time. But that's the difference of the difference, not the difference of the original, because you already computed that. Now you take these differences, and again, you subtract like the difference at period 2 minus the difference at period 1, difference at period 3 minus the difference at period 2. So you do that again. Now, it's the most common value will be d equal to 1, just by differencing once. But if required, you can, do it 2 times. Once we have found d, like let's say d is equal to 1 or 2, then we take that time series that has been differenced and we can plot the ACF and the PACF, not of the original time series. This has to be of the different series, like we saw yesterday. Okay, so this is how it looks. This is the differentiation effect. So on top here, we get the original time series. So you see that there are some patterns, right? It's decreasing, then it looks like certain level, but then it starts to increase. So when we apply the filter test, let's say that we do not reject the null hypothesis, then it's non-stationary. So we need to apply, we need to find the difference, right? So let's do D1. So we subtract yt minus 1, right? And this is what we get. This is how it looks, the time series, when we differentiate. So now it looks stationary. So you need to, again, apply the augmented decay filter to confirm that. If that's correct, if it's stationary, then just stop. I mean, you don't need to keep increasing D. And now you find ACF and PACF. We don't find ACF and PACF of the original tubes. We do it for the one that we have differentiated. Okay, so let's check an example. So we have the GDP of the US. This is US real GDP between the 1959 and 2009. So as you can see, this is not for sure it's non-stationary, right? And just by looking at the plot, you can see that the mean value is not constant. However, we need to apply the augmented decay filter to confirm that. So when we apply it, the p-value is 0.38, right? So remember, the null hypothesis is that the time series is non-stationary. Since we are not rejecting the null hypothesis, then the conclusion is that the series is not stationary, right? That was expected. That was expected. This is the real time series. Now, if you try to see the ACF, it will be something crazy like this, which makes sense because it's increasing. So it depends on previous values. So this is not useful. This ACF of the original time series. So let's find the difference, right? So when you do in Python, you do .diff, and that will help you to find the difference. You will do like yt minus 1. And now here is a label as growth, then GDP growth, because the difference, right, between two consecutive periods. As this is just a label, right? But again, here in the context of this problem, it can be understood as the growth. Okay, so now to a new time series, or the different after the differencing, we find or we perform the augmented decay filter, and the p-value it's close to 0. So we reject the null hypothesis that the time series is non-stationary. So that implies that actually it is stationary, right? So d equal to 1 works. So once we have found that it's stationary, right, after applying the differencing of 1, then this is how it looks, the new time series. Then now we can actually create the ACF and the PACF to see the structure, right? So remember, you can find P in the PACF and Q in the ACF. Now, when you're working with ARMA and ARIMA models, it's let's say it's more like trial and error. So you can find like candidates for P and candidates for Q. So for example, here, okay, like 0 and 1 always, but I can see that like 1 and 2, here we have positive values. Maybe not in 2, it's like on, like in the border, but you can use it P up to P equal to 2. In the case of Q, it's similar, 1, 2. So you have the candidates, right? You have candidates. So D is 1 for sure, and P and Q, they can be up to 2 in this particular example, right? So you can test different models here. So you see here. So in all of them, D is equal to 1. Remember that is P, D, Q. So D goes in the middle, is 1 for every single model. Or we're testing different values for P and Q, because maybe we find a model that complies with with Jumbox, right? With the assumptions on the errors. And since they might have less complexity, maybe they are better models. Okay, so we test all of these models. So in a for loop, we use our ARIMA function that hasn't changed, and the order is taken from this list here, right? Because we say, okay, order is in candidate order. That's a list that we define here with the candidate models. So we feed every single model and we store the AIC, BIC, and the Jumbox. And now we get, a list of 5 models, potential models. All of them are ARIMA. Remember, d is equal to 1. You see the 1 in the middle. The purpose is always to minimize AIC, BIC. That's what we want, right? So if we focus in this one, in the AIC, this is the lowest possible value among the 5 models, right? So this is a good model. Now, on top of that, when we check the Jumbox, the p-value is 0.45, so we do not reject the null hypothesis that the residuals are independent, which is fine. This is good. It's positive. Actually, most of them comply with that. The only one that is not good is the last model. This is not a good model because the residuals here are not independent. Okay, so once we have picked our model, this one, so we have here P, so we have autoregressive terms, right? We don't have Q, so we don't have residuals in the equation, like residuals from previous periods. So once we have our model, we can visualize the model, the parameters, constant component. This is the phi equal to 1 that multiplies the value of the previous period. We can write it down. This is how it looks, our equation. The constant component, and this is the 0.307 that's multiplied. This is the coefficient that we use from here in the table, right? Multiplying the term from the previous period, right? So here instead of W, this is YT minus 1. Okay, and as we just did, the residuals, we can analyze the plot of the residuals, the ACF, PACF, and you see that most of the values are, like on the shaded area. Some of them are on the border, but none of them are really outside. On top of that, you check the Jumbox for different values, say just 20, or you can do 10, 15, 20, as we did in our previous video, saying we get that again the p-values are greater than alpha, so we are complying with that, meaning that we can use our model for forecast. We just get forecast, and we get the prediction for the next periods. Okay, so this is how it works. It's very similar to the previous models. So just keep in mind that we use ARIMA when the time series is non-stationary. Now, there are some variations of ARIMA because so far we haven't discussed seasonalities in the Box-Jenkins context. But if there is seasonalities, there is what we call SARIMA with S, and that one includes seasonalities. Or we also have what is called ARIMAX with an X at the end. And that's when we have independent variables, like not just the time series, but we also have some predictors or potential predictors. So we can use an ARIMAX model to include independent variables. And sometimes that's helpful to make a better prediction of future values. Okay, I'm going to stop the video for now. I'll see you in our next lecture.